The best way to get familiar with chemical nomenclature, honestly, is to practice it. And so in this video, we're going to go through 4 examples of naming either binary ionic or binary molecular compounds. And as we saw in the last couple of slides, we have a process for naming these 2 different classes of compounds, but the first thing we need to determine is whether we're looking at an ionic or a binary covalent compound when we look at a chemical formula. And so to do that, we're going to consider whether the compound contains metals or nonmetals. Compounds that consist of metals and nonmetals are generally ionic, while compounds that consist only of nonmetals are generally molecular. So for example here, in the first example, we have MgClO42. Mg, or magnesium, is in group 2 of the periodic table. It is most definitely a metal. Chlorine and oxygen are most definitely nonmetals, so we're looking at an ionic compound here. And as we've seen, the convention in chemical formulas and in names for ionic compounds is to list the cation first and the anion second. The magnesium cation has a charge of +2. It's in group 2, and all group 2 metals form +2 cations. And so the name of that cation is simply magnesium, and according to our convention, we're going to list the name of that cation first. So the first part of this name is just magnesium. Now, what about the ClO4 bit? Well, this must be an anion to counterbalance the positive charge of the magnesium cation, and specifically it's the ClO4 anion with a charge of -1. Now, how did I know the charge was -1? Well, there are 2 of these ions for every 1 Mg2+. So the individual ClO4 ions must each have a charge of -1. If I don't remember the name of ClO4-, I can always refer back to our list of polyatomic ions and find it. This is right here, and that's the perchlorate anion. There are 2 of those in a formula unit of MgClO42. But actually, we don't need to worry about that in the name. Remember that because this is an ionic compound, we know there must be 2 ClO4- anions to counterbalance the positive charge of the Mg2+ cation. And so all we need to do here is magnesium perchlorate. No need for any Roman numeral on the cation, since this is not a transition metal. This is all we need in the name. In the second example here, we have Fe, that's iron, most definitely a metal, and we have Br3, that's bromine, 3 bromines, and bromine is most definitely a nonmetal. So here again, we're looking at an ionic compound. Let's actually write that down. This is the most important initial decision to make when you're naming a substance. Is it ionic or molecular? These first 2 examples are both ionic compounds. And to begin naming, we start with the cation, determine the name of the cation, determine the name of the anion, and just put those together. Fe here is simply iron. Now, iron is a transition metal cation, so we're going to need an indication of the charge of that cation, but I'm actually going to pause on this and jump over to the anion, since once we know the charge on the anion, we'll be able to infer the charge on the iron cation. Br is in group 17 of the periodic table, on the far right-hand side, 1 step away from the end. Because bromine is 1 step away from the end of the periodic table, it forms a -1 anion. The bromide anion has a charge of -1. And this means that the 3 of those that we find in this compound form a net -3 charge, meaning the charge on the iron cation must be +3 to counterbalance the -3 charge on those 3 bromide anions. And so we've inferred from the Br- charge that the charge on iron must be 3+, and we need to indicate that since iron in general might have a charge of +3 or +2 in ionic compounds, we do that with a Roman numeral 3. So the compound we're looking at here, FeBr3, is iron 3 bromide specifically, and that 3 Roman numeral is very important to include here. In our third example, we have a sulfur and 2 oxygens. Sulfur is a nonmetal, and oxygen is a nonmetal. So here we're looking at a molecular compound, right? two nonmetals bonded covalently. This is a molecular or covalent compound. I'll just write molecular here. To begin naming this, we again start with the name of the first element and the root name of the second, replacing the end of the name of the second element with "ide," since that's the more negative of the two elements here. So let's just start with sulfur. Let's just start with the name sulfur. That's the first element. The second element is oxygen, and remember, the end of the name gets replaced with the "ide" suffix, so we're going to delete everything after ox here and just replace it with "ide." But because this is a molecular compound, we're not done. We have to add prefixes to indicate the numbers of each type of atom in the molecule. There are 2 oxygens per molecule. We indicate that with a di prefix. And there is 1 sulfur per molecule. We indicate that with a mono prefix. And when mono shows up at the beginning of the name, this is sort of optional. You'll also see this compound referred to just as sulfur dioxide, since this makes things a little bit easier, right? If we use the convention that if there is no prefix, that refers to mono, right? We can do this for one number of atoms, and one atom is kind of the simplest place to put that convention. And so you'll hear this referred to as either monosulfur dioxide, which is completely fine, or sulfur dioxide. In the last example, we again have 2 non-metal atoms, nitrogen and oxygen, in the molecule. We've got 2 nitrogens listed first because that's further to the left on the periodic table, right, the more metallic element. And we have 5 oxygens, and those are listed second in the formula. This is a molecular compound since it consists of 2 non-metal atoms, 2 types of non-metal atoms. And the first element there is nitrogen. So let's start by listing the word nitrogen. The second element is oxygen, and as we saw above, we're not going to call that oxygen here. It's a little bit negatively charged, so we're going to refer to it as oxide in the name. And then we just need to add prefixes to indicate the numbers of each type of atom in the structure. So we have 2 nitrogen atoms. We'll indicate that with a di prefix. And we have 5 oxygen atoms, and this is indicated with a pent or penta prefix. Often, if the prefix ends in a vowel and the element starts with a vowel, we'll omit that vowel on the end of the prefix. This could also be called pentaoxide. That's completely fine as well, but pentoxide just rolls off the tongue a little bit better. So just to kind of sum things up here, we followed our processes for naming binary ionic and binary molecular compounds in this video in these 4 examples, but this determination of the type of compound we're looking at by considering the metallic or non-metallic nature of the elements involved in the compound is a really important first step, since that sends us down the right road toward generating a correct chemical name. We can also go in the opposite direction, determining a chemical formula from the name. And this uses the same conventions we've already discussed, just sort of in the opposite direction, thinking in the opposite direction. So let's look at these 4 examples. Again, a really important first determination here is whether we're looking at a name of an ionic or a molecular compound, and this can be inferred from the elements described in the name, right? Calcium, that's a metal. Cyanide, carbon, and nitrogen in that ion, those are nonmetal atoms. This is an ionic compound. We could, for example, use our list of polyatomic ions to determine that cyanide has a charge of -1, and based on calcium's position on the periodic table, the charge of that cation is +2. And to generate the formula from these ions, we put them together in a way that ensures electrical neutrality overall. So the formula will contain Ca listed first and Cn listed second, but we're not done. We need enough Cn minus anions to counterbalance the charge of Ca2+. And so we need 2 Cn minuses in the chemical formula. So CaCN2 is how we would read this formula. The name is calcium cyanide. The second example here contains ruthenium and oxygen. That's a metal and a nonmetal, so this is again an ionic compound. But now we have a Roman numeral after the name of the metal. This tells us the positive charge on the metal. This tells us immediately that this compound contains a ruthenium 4+ cation. The oxide anion, based on oxygen's position on the periodic table, 2 steps away from the end, has a charge of -2. And so again, to generate the formula here, we're going to put these ions together in such a way that electrical neutrality is ensured. We're going to need 2 O2 minuses with a total charge of -4 to counterbalance the +4 charge on the ruthenium cation. This is RuO2, or ruthenium 4 oxide, is how we would read the name. In C, we have silicon dioxide. Now, silicon is a metalloid, and so it's a bit ambiguous whether we're looking at an ionic or a molecular compound. Generally, though, when silicon bonds with oxygen, we're going to assume that this is a molecular compound and follow the conventions for molecular compounds. And in fact, the dioxide in the name points to a molecular compound, right? Since there's a prefix here indicating how many oxygens there are per silicon, right? Per one silicon. So we have silicon and oxygen in the formula, Si and O, and the di prefix here indicates 2 oxygens in the formula. So the chemical formula here is just SiO2. A little bit ambiguous whether that's a molecular or an ionic compound, to tell you the truth, because silicon is a metalloid, but nonetheless, we can use the conventions of the names and formulas to go from the name to the formula, as we've already seen. All right, in the last case, we have diphosphorus trisulfide. We have phosphorus and sulf in the name, indicating P and S in the chemical formula. The di prefix on phosphorus indicates 2 phosphorus atoms, and the tri prefix on sulf indicates 3 sulfur atoms. And this highlighting just emphasizes that the di and tri prefixes tell us the subscripts, the number of each type of atom in the chemical formula. So here, all we've seen is that we can apply the conventions we already know in the opposite direction to go from a name to a chemical formula. One lingering question I'll leave us with here is about compounds that contain more complex structures. What kinds of naming conventions do we need there? In fact, what we've discussed so far may give you the idea that from a chemical formula alone, we can generate a name. But there are substances that have the same chemical formulas that are very, very different in structure, right? A collection of atoms can often be connected in different ways to create different molecular structures. Those different molecular structures need to be associated with different names, since the compounds that those molecules find themselves in are often very, very different. There are more complex naming conventions associated with those types of compounds that you'll start to explore in organic chemistry if you study that subject.